specific to you are due tomorrow as well. All right, so I'm going to take questions on PS17 shortly. Does everybody have Kahoot pulled up? The computers are slow. Yes. Okay. Grab another laptop, please. Grab another laptop. Okay, then I can tell you guys about our lab. I don't think we're ready for that yet. Who is on Kahoot? Raise your hand. Oh, good. Like 7 of us. Okay, great. Okay. Well, then let me go over some questions on PS17 first. You guys want to tell me? Yeah, what to go over?
9.
Hold on. I have it pulled up here. I think I have it. Oh, before I do that, can I go over the true false? Yeah, true false. Here you go. Check this. Not true. Ready? This is more conceptual understanding of the math side of things. We do a lot of the math in class, not necessarily talk through the conceptual side all the way. Not true, always true. Not true, always true. Always true, sometimes true. We're on number 6. Number 7, always true. 8, always true. 9, always true. 10, never true. 11, always true. 12, never true. 13, never true. Let's talk about the ones you missed. Give me a heads up on which ones you missed. 11 and 12. I'm going to give everybody one more shot at trying out this. Give me a hand up if you're on Kahoot. If you'd like, tabs on that. If you have not even clicked the internet icon, then you should click the internet icon. Okay, so let's do 11 and 12 right here. 11, in order to convert 1 mole of water liquid into 1 mole of water gas, 40.7 kilojoules must be supplied. So that is actually a constant. And so the 1 mole of liquid to 1 mole of gas, liquid to gas, that's a phase change example, right? And on our little blue sheets, they give us as the delta H vaporization, not in kilojoules and moles, but they give it to us in joules per gram, right? That actually is equal to 40.7 kilojoules per mole if you were to convert. And so that's why I said sometimes they'll give it to you in grams, sometimes they'll give it to you in moles. So that's an always true. Maybe it depends on what you think about it. It could be sometimes true if you're trying to think about it in this reference in terms of joules per gram. 12. When ice melts, the temperature of the ice increases until the entire sample becomes liquid. First of all, ice melting is a phase change. Does temperature change during phase change? No. So the temperature of the ice is not increasing as it becomes liquid because it's just a simple phase change. Another one up here, guys, conceptual stuff. Speak now. 5 and 8. Okay. Calories defined as the quantity of heat to raise the temperature of 1 gram per by 1 degree Celsius. So yes, that is true because in terms of the specific heat capacity of liquid water, what is the specific heat capacity of liquid water? 4.18 joules per gram degree Celsius. What does 4.18 joules equal? Yes, 1 calorie. And that's a conversion that we kind of have understood to be similar in units because it's energy and energy, but I could easily express this as 1 calorie per 1 gram degree Celsius. So that means that that's definitely, what we use in our nutrition labels. But that means it takes about 4 joules to increase 1 gram of water by 1 degree Celsius. And that differs for everything. What kind of materials have very, very, very low specific heat capacities? Metals, because they gain heat really fast and they lose it very fast, which is nice if you're trying to actually handle the metals themselves. And then I heard 8. In endothermic reaction, the potential energy of the products is higher than the potential energy of the reactants. What are you visualizing in 8? The graphs. What kind? Like we've got a bazillion graphs. You gotta be really clear on which graph is for which topic. So no, it's not the heat curve. The heat curve is the one that's not a curve. Remember? The heat curve looks like this. That is not what we're talking about here. We're Draw it in the air. It's the hump one. We'll call it the hump one. Okay. So it looks like this, and the labels are the axes are potential energy and time, or reaction progress. Sometimes is what the I want to say denominator, the x-axis is. But yes, potential energy in this case, as described here, the potential energy of the products is higher than the potential energy of the reactants. So that is a true statement, always true, and that's what I mean by endothermic, because the example here shows an incline, an increase in energy of those products. That's our delta H. Some more conceptual stuff, guys? Okay, who's on Kahoot? Awesome. Okay, let's make sure we're there. And then let's make sure InLove has it. Hold up, there it is, okay. Alright, so you guys see enthalpy? Enthalpy pirate. Feel still your jewels. You know that's funny. Okay. Only 8 questions, it's real fast, okay? Classic. Ready to join? Yes? Because we're on our Latte Puppies? Put a name that I can recognize you by. No Beyonce's in here, okay? Unless it's Jacob. Jacob, you can be Beyonce. Gosh, there's so many names. Okay. I got 24. Megan. Sounds about right. You don't need that. I got to put it over there for you in case you need to. Okay. Are you ready? 8 questions. This will be a nice one. You have your folder out if you need it, okay? Endo or exo? You gotta look at this information though. Okay. Thank you for people asking questions. How did we just get that wrong? Literally 30 seconds ago I went over this with you. Pay attention. Endo and exo, what's the exothermic curve look like? It doesn't have to go to the very bottom, but simply we have a difference in energy, right? So endo goes up high, exo goes down low. Okay? We release energy or we absorb energy. Does temperature measure potential energy or kinetic energy? Okay, so what's the definition of temperature, guys? Average kinetic energy. You got it? You got it. It's on the back of your foldable. Solve. Math. Calculate the initial temperature of a cup of coffee that cooled down to 20 degrees Celsius if the overall delta T was negative 34. You really should need a calculator, but I get it. It's 7:30. Maybe way too much time. Jumpstart your brain. You essentially do. It's a device. Alright, give me 10 seconds. Okay. Ooh, it should be negative 54. No. Okay, pause. The delta T was negative, meaning that final minus the initial was negative. So the final was what? What was the final temperature? It said it dropped to 20 degrees, right? So how did it drop to 20 degrees? It started off at 54, okay? And so it lost 34 degrees. But let me do it the right way. T final minus T initial equals negative 34. So the difference here is negative because I dropped to a lower degree. Does that make sense? The change in temperature can be negative, but most time masses are not masses are never negative, and delta T or C values are never negative. Okay, good talk. If you're dropping in temperature, it's going to be high to low, so your initial temperature is going to be higher. Okie dokie. Solve. Calculate the heat given off when 122.9 grams of copper cools from 178 degrees Celsius to 74 degrees Celsius. The specific heat capacity of copper is 0.385 joules per gram degree Celsius. Okay, so let me give you a tip. This did say energy release, so some of you guys are probably thinking, do I need to put the negative or not? But when you calculated, it should have been a close to this number, true, okay? And so that double kind of verification that's showing as a negative kind of indicates to you that's the release nature of it. So I think most work's pretty good there. I'm happy. What did you have to do? Q equals MCAT. There you go. Nice. Solve. I mean, I've got two more like this. Calculate the heat necessary to raise 48 grams of water from 97 to 190 degrees Celsius. Specific heat capacity of water is 4.184 joules per degree Celsius. It's a nice calming song. But I took the AP exam last night. It wasn't that bad. I don't know. I mean, I have to guess whether the quiz fall because they don't release the rubric until like August. So I think I got a 5. I should have, right? And you guys actually could do one whole question. I know. There's one question here. I was like, it's totally Thermochem. You guys should be able to do it. Oh yeah. Basically we do everything to a higher level. Okay, so negative? Whoa. Right, we are raising in temperature, right? So you have to add that. That should be positive. Now, I will qualify one thing here. What should we have had to do as well as what we did here? Well, okay, yes. But this went from 97 to 190, right? So really, and I kept this simple, most of you guys just did MCAT, right? About what really happened here. I'm going to start at 97. What's happening here? And we went to what? 190? Yeah. So we should have done this plus this plus this. Right? But I told you just the C of water liquid, and we assumed that it was the same all the way, but it actually is not. So I just wanted to give you a heads up. We could have done something slightly different there. What is the melting point of the substance due to, or according to the phase diagram? Fast question. It says phase diagram. I copied this from somebody else. Just let you know. Usually don't make my kids duplicates. Okay, what are you looking for? The change between what and what? Solid and liquid is the first little vertice thing. So, yes, where are we at 15? Were we looking at vaporization? Yes. Okay, so it should definitely be the first plateau. Next, which region of the diagram shows only potential energy increasing? All right, last three people. Ooh, yes. Okay, very good question, which 7 of us got right. What is it actually asking?
Where does it plateau?
Where does it plateau? And why during the plateaus? Right, so during this change, and this change, what's changing? Temperature, right? What's the measure of temperature one more time? Average kinetic energy. So on those sections, it was all kinetic energy changing. So just potential energy changing is here. And why is potential energy changing? What is potential energy? So it's related to the inherent energy that the particles kind of just naturally have that it could potentially put out into the world. So talking about actually spacing. So particles that are really close together have a certain amount of potential energy based on their interactions through intermolecular forces, and then they're farther apart. They have changed their potential energy because now they have a different kind of inherent intermolecular force of attraction. So anytime during phase changes, your potential energy is changing, but not kinetic energy. Last one, solve. Now you got to get close. This one's a little tiny picture from memory. Sorry. Let me read this out loud. Determine the number of kilocalories of heat produced from the reaction of 100. Do not take pictures of the cahoots. Just get going. Produced from the reaction of 15 grams of calcium oxide. So you may have to look at the equation first. Calcium oxide plus water yields calcium hydroxide and 15.6 kilocalories. Think about your given. Think about where to proceed. I see a lot of us writing stuff down. That's probably the first step. You need to chat with a neighbor, I understand, but you need to get going. You got 70 seconds.
Ooh.
You got an answer on the board? You should be good. Two people. Who knows what they're doing? Okay. Quick circle.
Let's just choose something.
No, do the math.
5 seconds.
Oh yeah, you do have 3 seconds.
Ooh, I got it right! I got it right!
I know. So, you got it right?
I got it right.
Did you know what you were doing?
No.
Oh my goodness. Okay, so calcium, what was the reaction? Write this down in your paper someplace, okay? Calcium oxide, which is what?
CaO.
CaO plus H2O yields CaOH2, which is, speak my language, calcium hydroxide. Is this balanced, yes or no?
Yes.
Yes. Okay, so I gave you the spaces, but you just had to quickly look. Calcium, 2 oxygens, 2 water, or 2 H's, 2 H's. That whole process released 15.6 kilocalories. Is that right? 15.6. It starts you off with what? 15 grams of who? Calcium oxide. You can't do crap with that. What do you have to do? Convert to moles. What's the molar mass?
56 grams.
56 grams. You just took 40 plus 16, right? Approximately. We have pretty different answers here. You didn't have to get too specific. Okay, so we converted to moles, and now we can look at the mole of calcium oxide and correlate that with what? The amount of kilocalories that are released, because it's basically like a mole ratio. So I can then say 15.6 kilocalories is released for every 1 mole of calcium oxide reacted. So 15 divided by 56 times 15, that's about 4. Yeah, so 4.18. 1726. Why we got 48? Yeah. Okay, so that's it. There you go. Let's see how we did. Get the results. Boom! I'm going to download these results to see where your deficiencies are. You guys can make feedback, comments, and so forth. And I'm going to show you the next part of our lesson for today. Oh, I heard number 9. What else from? 7 and 9. Okay, I'll do these quickly. 7 and 9. Okay. All right, so 7, how many moles of ammonia can be melted by the addition of blah, blah, blah heat? Okay, so we're talking about melting. So when I first read this, I'm writing moles of ammonia, and it says melted. So what do you think of when you hear melting? Delta H diffusion, right? So there's little keywords that could they're supposed to serve as triggers. I hear melting, I think of fusion. I think of delta H diffusion. I think of phase change. So you're thinking of the phase change equation. When Q is equal to 250 or 0.56 kilojoules of heat. So we'll get to this volume question in a second. So I'm looking for moles. I have the delta H diffusion given to me on the problem set that I said take a picture of for ammonia. Ammonia, oh, where's it at? Ammonia, right here. So you have that data point, which is not one that is on your reference table. I had to pull these out of the book for you, but you guys have your book for that reason as well. So you have 5.65 kilojoules per mole. This is 5.65 kilojoules per mole. What equation can we use to solve for moles? Say again? Right, I can either do the mass times delta H diffusion, or I can do the other one. The moles times delta H diffusion. I'm going to do that one because I'm looking for moles right now anyhow. So the Q is equal to moles times delta H diffusion would be what you're going to start with. What are you going to isolate? Moles. So to divide by what? Delta H fuzz. Delta H fuzz. Okay, and then we're going to put Q divided by delta H fuzz, and what do you get? Any takers? So 200.56 kilojoules divided by 5.65 kilojoules per mole. Kilojoules cancel, and you get it. Say again. 35.5 moles of ammonia. Okay, so that part, assuming you see the Q and you see the delta H diffusion, and you start to realize that's your one equation, that's probably the easier part. What about taking, assuming, ammonia can be a solid, liquid, or a gas. Ammonia is what cat pee smells like, or cat pee smells like ammonia. It smells great. So if we're talking about it being a gas and talking about volume, you're going to be talking about what unit in particular? Liters. And when you hear STP and you think of gases, you already think of what constant? 22.4 liters per mole. So I have moles, right? So take those moles, 35.5 moles of ammonia, and assuming STP conditions, what can I then use here? Say what on top? 22.4 liters over 1 mole. So what is this? 796 point what? 0.2 liters. So 3 sig figs would be 796. Okay. That's just a little bit of gases thrown in there to keep you on your toes. And then I heard number 9. Okay. So this was, I think I left you with this tip before you left. What did I tell you the boiled 9? And that's my what? So again? It says a sample of metal is boiled. Stop. Oh, okay, so metals, right? We have to put them in hot things. I can't put a metal in the microwave. What would happen? It would explode, right? You can't put metallic things in the microwave. Note to self for future. So when it says it is boiled in water and then placed into blah, blah, blah water, this is basically telling me that my metal's temperature initial is 100 degrees Celsius, because we're assuming that if once the metal is in boiling water, it's going to kind of take on that same energy, take on that same heat. So I have the mass, I have the temperature initial, and have some other information. So I know you guys have been organizing your data very well. Tell me the data that you're given here. Metal versus water. Metal was what? Okay, and water was? And how do you know that? Right, the density is 1 gram per 1 milliliter. Okay, so that's 75.0. What's my C of water always in liquid form? Thank you. 4.18 joules per gram degree Celsius. What's my C of metal? Finding that's our question here. What's my delta T for my metal? How are you doing the math? Okay, so the temperature, the other way, right? Temperature final minus temperature initial here. What's my temperature final of both things? Okay, and so that's my final for both. What's my temperature initial for the metal? Now I'm talking about metal first. Right. Because the metal is initially boiled in this separate pot of water, the initial temperature of metal is 100. Everybody ends at thermal equilibrium, so everybody ends, so meaning the water in the calorimeter and the metal, both of them end at 55.2. So you're doing what minus what? 55.2 minus 100, which is what? 44.8, right? Okay, just making sure, mental math. Okay, so that's our delta T for the metal. What's our delta T for the water that's in the calorimeter? Where does it start? Starts at 40 and ends at, so we're doing what minus what? Minus 40, so what is that delta T? 15.2 degrees Celsius. Okay, now we're going to use all of that. We're going to set what equal to what? Q equals to Q, right? Because we know I could use this to find Q for the metal, and I can use all this to find Q for the water. So that means that we're identifying the metal and the water as system versus surroundings. And a picture like that would be basically we're taking a piece of metal and we're dropping it in, that's our metal, we're dropping it in some water. So what would you consider the system? Well, if you have to identify system versus surroundings. The metal is probably our system, and our surroundings, which is all around it, is our water. So it's just showing you the exchange between thing 1 and thing 2. All right, so who's losing energy? The metal, because it's decreasing in temperature. Who's gaining energy? The water, so you get a positive there. So I can't do anything with Q, because I don't have either Q. But I could actually solve for the water's Q if I really wanted to. I prefer just to set MCAT equal to MCAT and then go with the flow. So MCAT equals to MCAT. Which part of this MCAT stuff am I solving for? C of what? C of the metal. How do I isolate this C? And the negative, right? So C of metal is equal to what setup? Variable-wise before I start plugging in. I'll put the negative on the bottom in a second. So I'm dividing by a negative M in delta T. So it's all this, right? C of the metal is equal to MCAT for water. That's all the water data here. Divided by what? Negative MAT. Negative M delta T for the metal. Plug it in, plug it in. What do you solve for? C, and then how much you get. I'm not plugging it in. You can plug it in. I know you guys have most of your data on your paper already, I would hope. Any shakers? Yes, 2.62. This metal is a funky metal. Why am I saying it's funky? Pretty high for a specific heat capacity of a metal. And it's probably because it's an enlomative example. But it generally is going to be like 0.2, 0.4, 0.6, 0.3. A couple of them are at ones, but very few metals are high like that. And why is it still joules per gram degree Celsius? Because the specific heat capacity should be those units. And you can actually cancel those units out as you go. Everything but that again. Okay? All right, so I'm going to pause on Thermochem. We are moving on in like 30 seconds, okay? All right, so that gave you a lot of opportunities to ask me and bring you to. I'm going to show you that this laboratory is going to take some effort in reading. And so the beginning has to give you an idea to look at in terms of system versus surroundings. And so talk about spontaneity. So if we're talking about spontaneity, that means that you're reflecting back on delta H and delta S information. But a lot of the reading is in here, okay? The lab has about 3 or 4 parts where you're going to be dissolving things. When we're starting to dissolve things, that means we're actually jumping into our next unit, which is solutions. What 2 things make up a solution? Solvent and solute. So you'll start to kind of utilize those terms as needed. You'll actually draw some particulate diagrams and so forth like that. So because I know a couple of you guys are going to be in and out, I did this so I could start part of it today and part of it tomorrow. There's some clean break points here. I'm thinking it would be best to do it in groups of 2. Okay, groups of 2, maybe 1 or 2 groups of 3. Especially if you know you're going to be gone tomorrow, then I would group those people so that you guys can kind of stop and start at the same places. Okay? So, get a piece of paper out. Let me tell you what, oh, hold on, before you do that, let me tell you what you're going to do. That I'm giving you guys digital thermometers, and it requires you to get used to using something called Logger Pro, which you may have already seen on the desktop computers or on your laptops themselves. Logger Pro is a software that's kind of just mainly for chemistry, physics and other things, and you put little probes and you tuck them into the USBs of the computer, you hook them up with a Go link, and you pull up this Logger Pro software. It's on your desktop, it's an icon. So it's just going to get you used to kind of more of the digital side of things in terms of science. But you'll start by reading ahead, and then I'm going to give you guys one either ammonium nitrate or ammonium chloride to start with. And that's going to be kind of your beginning. I don't think I really need to explain it because you guys can read. Okay, let's roll. Get a piece of paper. Choose people wisely. If I told you before that I don't appreciate you choosing your group because you're classes, then do not choose your people again. That's going to who you are. Okay, let's go. I'm going to choose that copy that we did now. I can't add more.
Actually, no. You gonna be here tomorrow? Yeah. Bradley gonna be here tomorrow?
You eventually will need goggles. Start reading. I can have another group over here. You see, bring on laptops. Have one group already using a desktop. Raise your hand if you're an AP testing tomorrow. Guys, need to start reading now. Start reading in your groups now. You will want to write down some information so you don't have to keep rereading that paragraph 15 times. Write down little pieces of nuggets of gold. And write down nuggets of information.